So just a brief introduction about myself. A couple of years ago, I finished my PhD in maths, and since then, my day job has been in a company in Madrid doing satellite navigation receivers, mainly for GPS and Galileo. So I do signal processing for the receivers. But besides my day job, I've been doing since several years ago many different projects in radio communications, amateur radio, and space science, spacecrafts, all those kinds of things. I hold a couple of amateur radio licenses, the Spanish one and the UK one. And you can see about my experiments on my web blog or in Twitter. So just a brief outline of my talk today. I'm going to introduce what GR satellites is and its main features. Then, since this is GRCon, I want to take a brief look under the hood of GR satellites to show how I do some of the things, maybe to show some useful features that you can reuse in your projects, even if they don't have anything to do with satellites. There are blogs which can be useful for very general things. And also so that I can get some feedback about what things can I improve or do differently. And then a quick look to the future with the roadmap and a quick demo. So GR Satellites is a unit radio out of 3 module with a collection for decoding amateur satellites. So with amateur satellite, I understand any satellite which transmits data on amateur radio bands. These are satellites made by amateurs, also satellites from universities who are doing educational or research experience, and also some satellites made by small companies, startups, or research institutions. So basically, for each satellite, you have a flow graph whose inputs are IQ RF samples, either taken in real time from an SDR hardware, or a conventional radio, I don't know, an ICOM transceiver or something like that, or a recording. And the output is packets in hex format, or raw telemetry values like this voltage, this intensity of the current, so on and so forth. Currently, it supports more than 80 different satellites. Many of these are very much alike, so they use very similar protocols, but others are quite different, and they use ad hoc protocols. It has a lot of different blocks. Many of them are in Python, but also some are in C++. And the main goal of the project for me is to provide an open source solution so that anyone can decode every satellite which transmits data on amateur radio bands. So I try to focus on these satellites which don't have any other available software. There are some satellites, such as the AMSAT North America Fox satellites, which have really good software. So I don't have a main goal to support those, only the other ones which are not supported elsewhere. I'm essentially doing this on my own, but I'm eager to collaborate with anyone who is interested. This started in 2015 as some series of experiments where I tried to decode satellites that no one had been able to decode before, of course, other than the satellite operators. And I had to do at least some degree of reverse engineering to decode this. I did this mainly for learning and for fun, but another important motivation for me is this sentence in the ITU regulations about the amateur radio satellite service, which say that transmission by amateurs shall not be encoded to obscure the meaning. Effectively, what this means is that any transmission on amateur bands needs to have open specifications or an available decoder or some form that anyone can go and decode the data. So I think that this concept of having open standards or open specifications for radio communications can be tied very well to this notion of open source spectrum that Mark Shuttleworth was mentioning yesterday. And since people started to find this kind of experience useful, I decided to collect all of them under a collection, and this gave birth to GR Satellites. Since then, I've been adding supports to new amateur satellites as they get launched. So usually, the development goes like this. A new satellite is launched. Some amateurs are interested and do recordings of the satellite signal. And then I look at the recordings. I also search online to see if there are any documentation or specifications about the encoding protocols, etc. used. Usually there's not very many documentation, so I try to work in parallel with contacting the satellite team to try to engage into the conversation with them and get some data, and to reverse engineer on my own. Usually I need some amount of reverse engineering. It changes between different satellites, but the main problem is that sometimes I don't get any answer at all from the satellite team, or many times they don't have complete knowledge of the protocols they are using, just because they are using a commercial radio, maybe with the default settings, and they don't know much about digital communications. But if all goes well, in the end, we figure out all the specifications, so I can write a decoder and add it to a collection, and usually put up a blog post explaining some of the interesting technical features. So a few words tying about open documentation. Currently, there is an ongoing discussion within the amateur radio community to make stronger requirement to those using amateur radio spectrum for satellites to publish open documentation or software so that anyone can decode the signal. And so if you are designing any satellite with the plans to use amateur spectrum, please get in touch with the amateur community. We're here to help. And please be able to write and publish good documentation. So a brief look inside. As I mentioned, every satellite has a different GNU Radio companion flow graph, and the basic information about each of the flow graphs is included in the README file for the project, saying the type of modulation, for the correction, encoding, and so on that each satellite uses. The flow graph contains the telemetry decoder, whose goal is to get from IQ samples to PDUs containing the data frames or the protocol frames. And then, depending on each particular satellite, it can have telemetry parsers, which decode the data into readable numbers, such as voltages, temperatures, and so on. This is done using a very useful Python library called construct, which can parse binary data and also build binary data. And some of the satellites transmit another kind of information, such as JPEG images. So some of these decoders have image decoders, which reassemble the images. The flow graphs don't have any GUI. This was a design choice so that it can be run on a headless environment, on a remote Raspberry Pi, or whatever. There are some command line configuration parameters. So the main idea is that you run this using the Python script that you get from the GRC file from the terminal. There you can specify parameters. And the output gets printed to the current terminal or passed on with sockets or files. About the input format, anyone who has the need to support different formats for radio stuff can know that this can get really cumbersome, because there are different sample rates, different sampling formats, IQ, real data, and so on. So to keep things simple, I decided to settle on one single format for the input for almost all of the flow graphs, and this is real-time UDP input using a real signal. So this is a single channel, floating point 32 bits at 48 kilohertz, so the usual audio sampling rate. The main reason for that was that GQRX, which is this popular SDR application, already has a feature to stream the audio using this very same format. And also many people have recordings taken from conventional radios using the audio sound card on the computer in this format. So depending on the modulation of the satellite, something different is expected as this kind of audio signal that you input into the decoder. If it's an FM or FSK signal, you need FM demodulated audio. So the kind of audio you would get from setting your ICOM or YES or Kenwood radio in FM mode. This is so that you can use a conventional radio also for this kind of modes. If it's a narrow bandwidth linear signal, for example, 1.2 kilobaud, BPSK, you need to feed in a conventional SSB audio, so from 0 to 3 kilohertz passband, with the signal in the middle of the passband, again, so that you can use your conventional radio. But there are also some wider linear modes which don't fit into the conventional SSB bandwidth, such as 9K6 BPSK, and for that, you usually need to use an SDR software, and what the decoder there expects is to have the wideband signal in a 0 to 24 kilohertz bandwidth centered in the middle of the passband. So, as I said, the different ways to feed input is to use GQRX or GR frontends, which is a small collection of very simple GNU radio flow graphs that take data from a variety of sources, a WAV recording, the audio sound card, or some SDR hardware, and stream it using this UDP protocol. And of course, you can build your own using Netcat. This is what one of the flow graphs, looks like. And in here you have the UDP source where the data comes in. I don't know if you can see the mouse, yeah. And then depending on the signal, you have some signal conditioning and decoding. So for this particular satellite, the signal is audio frequency GMSK. So there is first some frequency shift and filtering for the signal, and then the GMSK demodulation. Then there is this sync and create packed PDU block, which I'll talk about later, but essentially it locates sync words within the data and extract the packets. You have auto correction, and finally, when you arrive to the packets, you have a telemetry forwarded block to send the telemetry frames to the SAT-NOX database. So this is an online application which can collect telemetry frames from many different satellites. And also you have this telemetry parser for the specific satellite, which parses the packets, get the telemetry values, and prints those onto the screen. So talking about this sync and create packed PDU, or not packed PDU, I see that this is a question that often pops up with newcomers to GNU Radio. Okay, I have a simple protocol, and this works in the following way. It has fixed length packets, maybe, I don't know, 100 bytes, and at the end, at the beginning of each packet, it has a fixed sync word, 32 bits, for example. How can I run my FSK demodulator and extract the packets? So for this kind of problem, I created this sync and create PDU block. Just because there are many different protocols, not only for satellites, which use either packets of a fixed size or of a variable size, but with a maximum which is not so large. So even if the packet size is variable, extracting packets with a fixed size anytime you detect a sync word is a valid approach. So this is what sync and create PDU does, and it allows overlapping packets. This means that if one of the sync words is here, and I want to extract 100 bytes after that to create a PDU, it doesn't matter if I have a shorter packet and the second one starts here. I'll get one PDU with this and another PDU with that, even though they overlap. This is useful for shorter packets, so packets shorter than the MTU, and also in case you get false sync word detections so that you don't lose any data. The way this works is through a hierarchical flow graph. So you have before this correlate access code tag, which is stock GNU radio block, that locates the sync word and just puts a tag in the stream whenever it happens. Then this is a custom block in Python, which locates the tags and turns this into a tagged stream. So if you want unpacked data, so this is 1 bit per sample, then you are okay, and you can just do tag stream to PDU to get the PDUs. But if you want packed bytes, so this is 8 bits worth of data into each sample, you can do this sort of transformation to pack the bits and also, of course, transform the packet length tag accordingly. So this is the way I came to solve this kind of problem several years ago, but I don't know, there are many other possible ways. Perhaps I should look into using protocol parser for this. Many times you want to work with packetized data through a stream of bytes. For example, maybe you have some frames that you want to save to a file, or maybe you want to transfer those through TCP. So KEYS format is very useful for that. Originally, the KEYS protocol was used to interface with a packet radio modem, but it is just a very simple way of using control bytes to mark the frames of packets, so packet frame boundaries, inside a byte stream. So for this, you can use the PDU to KEYS and KEYS to PDU blocks inside GR satellites. For example, let's say you want to save some PDUs into a file. You can plug your PDUs in here and send this to a tag stream of bytes and to the file sync. And to recover or to read those PDUs, you just hook up the file source into the KEYS to PDU block and recover your PDUs. HDLC protocol. GNU Radio already has some default HDLC framer, anti-framer blocks in C++, but I have my own deframer and framer in Python in GR satellites. And these have some interesting features that the ones in GNU Radio don't have. So this is a comparison on the top row. There are the blocks from GNU Radio, and on the bottom row, we have the blocks from GR satellites. And the main differences are that on the framer, in GR satellites, you are able to specify if you want many preamble bytes or flags, these 7E, famous HDLC flag, and how many post-amble bytes you want. So this is very useful because when you're working over the air, so when you want really to work with a receiver, you need to transmit several times the preamble so that the receiver can log onto the clock of the signal. And I think the HDLC framer on GNU Radio only inserts this preamble once, so this is rather short. For the deframer, the main new feature is that you can skip this CRC checking. So, of course, you'll get a lot of garbage, but when debugging things, it is sometimes useful to disable the CRC check. For example, there are some of the satellites where the CRC NDNS is not correctly implemented. So it is useful to look into that. Some other components which you might find useful, these are more specifically intended for satellites or space communications. There are decoders for the GOMspace radios. These are very often used in small satellites, such as CubeSats. I also have decoders for the Texas Instruments and Silicon Labs FSK chips, such as the CC11 family and these 4463 Silicon Labs decoder. These are not only used in a few small and inexpensive satellites, but also in many different short-range devices, such as garage door openers and things like that. Of course, several different fault error correction decoders, CCSDS, using Phil Karn's very nice libfec, and also using RS code, which is probably redundant. It could be done the same kind of decoding using Phil's libfec. Also BCH decoder, Golay, and so on. And there are several descramblers for use of protocols, and CRC checkers for CRC16, CRC32, etc. So about the roadmap, things that have happened earlier this year. During June, I did a small contract for a startup company in Poland, which is called Sat Revolution. And within this contract, what I did was to adapt GR satellites for their 2 satellites that they launched through the International Space Station, I think in May or something like that. They were released in orbit in July, at the beginning of July. So, of course, this is not my main goal when developing GR satellites, to work freelance for companies. As I said, I do this for fun, for learning, and also so that anyone can decode amateur radio satellite signals. But I think that this shows that GR satellite has become a useful tool also for companies, and that since there are already many things implemented in GR satellites, this lowers the development costs significantly. So I only needed to do some new blocks to add these blocks to GR satellites for the Sat Revolution project, and could reuse most of the components of GR satellites. Of course, the outcome of this project has been published under the GPL and is on the GitHub page of the project. During the summer, I've been participating in the ESA Summer of Code in Space. Ben already mentioned that on Monday. So Athanasios Thecharis from Thessaloniki in Greece has been adding blocks to GR satellites to support different protocols in the CCSDS framework of standards. So these are protocol standards not only used in low Earth orbit satellite missions, but also used for deep space. And there is a poster about Athanasios' work hung there in the poster session. So, speaking about future developments, currently I haven't ported anything to GNU Radio 3.8 or Python 3. I plan to do this probably when I get back home from this conference. Mainly the reason that I haven't ported this before was so that Athanasios was working already on the 3.7 version, so I didn't want to change things radically through the ESA Summer of Code project. But this project is also coming to an end next week, so probably GNU Radio 3.8 will be supported during next week or maybe by the end of September. But I'm also planning some larger changes. One of the problems I find is that GR satellites has grown enormously. It started with very few satellites, and now it has, as I said, almost 80 or maybe more than 80. So it's crazy stuff to have a different flow graph for each of the satellites. If I want to change a particular parameter for the FSK demodulation, for example, this is used in maybe 60 different flow graphs. So it's impossible to go and change it in all of them. And as you can imagine, many satellites use the same kind of forward error correction or modem or things like that. So there is a lot of repetition between different flow graphs. So I would like to take a more modular approach to try to solve all this repetition, and also so that it is easier to add a new satellite just by doing some specification of what's the modulation used, what's the kind of radio or protocols, and that then the decoding chain would be automatically built by taking those components. I also would like to support more flexibility with the outputs so that you can enable and disable what gets printed to the screen, what gets redirected to which files, and so on. And also more flexibility with the inputs. Okay, UDP real-time input is fine, but if you have several recordings, and maybe those are 10 minutes long, processing those in real time is quite boring and cumbersome. So what we need is for a way to be able to process recordings faster than real time. Perhaps it would be good to add some GUI components so that people can already have some feedback about the quality of the signal and things like that. And I'm also open for any kind of suggestions about what would you find useful. The main problem with this is that it will change the way that current users interface with the software. So I really need to speak with the community to find something that is useful for everyone and that not breaks the way that people are used to doing things. I also would like to try adding some FSK demodulators by David Rowe. These work on the IQ signal rather than on the FM demodulated signal, and by doing so can achieve better performance by filtering the different side lobes of the FSK signal. I also want to add some tests. With time, I have compiled a collection of short sample recordings from different satellites. So what I need is for a way to run these recordings as end-to-end test of the decoders to be sure that during an upgrade, nothing is broken. I'm not completely sure how to go about all of these. So as I said, comments are welcome. And I'm also not sure when I'll be able to do all these tasks, since GR satellites, I usually say it's my largest project, but it's also kind of side project because most of my time not goes to GR satellites, but to many other smaller and varied projects or experiments mainly having to do with amateur radio and satellites. So let's go for the demo. What I have here prepared is the LilacsHawk1 GR satellites decoder with a recording that transmits a JPEG file image. So I can start the decoder and the playback like this, and some packets will start in a moment. So LilacsSat was a Chinese amateur satellite launched in 2017, if I recall correctly. From the International Space Station, it orbited the Earth for about 1 year or so, and then re-entered in the atmosphere. And I promise the signal is coming. I tested this yesterday. So there we see some packets already. The decoder is counting packet number 0, 1, so on. And we see telemetry data. I think it's too small to see, but you can see that each packet is broken up into different values, and this gets printed on the screen. So let's see if I can display both. And now the image is incoming. We can see image packets. It says packet number whatever, camera. So the image JPEG file is transmitted at 4.8 kilobits per second, as in the old days of the internet. And it takes a while to download the small JPEG image. But you can see that the decoder is updating the image in real time as new pieces of the image come. And all of this, besides displaying the image, is done inside GNU Radio. So the only external component is this image viewer called FE, which just keeps refreshing the JPEG file, which is in the hard drive of the computer. And it's a block in GNU Radio, which is finding where to store each of the blocks of the image and keeps updating the JPEG file in the hard drive. So with this, my presentation comes to an end, and I'll be happy to answer any questions. Thank you.
Question? Okay, you're still thinking about your questions, and I'll just ask one myself while you're... I myself, and I think others in this room, believe that open source implementations should be actually the publication of standards. So, and then that's kind of what you're doing. You're saying, okay, like, there's no published standard for this and that satellite, so I'm just going to write the code, and then the code kind of becomes the standard. Is that something you intended? Do you agree with that statement? Is that how would you feel about GR satellites being like something that people reference as when they say, okay, like I want to know how this particular satellite works? Like, how do you feel about that?
Yeah, I completely agree with your comment. So in one way, if you have the open source code to work with some protocol, this is already a documentation about the protocol or the standard. Of course, just writing code is not the best way for people to understand how protocol work. Imagine if all the internet protocols were not written in RFCs, but rather you are given open source implementations. This would be really messy to study. So this is the reason why for the most interesting parts of the protocols, I also write some blog posts about it. But I also think that open source is a complementary good documentation for open protocols or standards. Since if you have the code, you can test it, you know it already runs, you can adapt it for your application. So in some way, it's complementary to a PDF file describing the standard. And it's unambiguous, yes. So you have something, some sample data and some code which works with the data. Thank you very much.
And thank you very much as well.